You are standing on a miracle only a few atoms thick. Above you is space. Below you is a churning engine of rock, water, air, and life. This world builds mountains, turns oceans into clouds, and rewrites the sky. Tonight we follow four engines: inner heat, drifting plates, restless oceans and air, and life itself. We will see how Earth makes and remakes us. Before we begin, if you have not subscribed yet, please tap subscribe, like the video, and share your thoughts in the comments. Thank you. Now let us begin. From the quiet edge of orbit, our world brightens beneath us. Beautiful, yes, but powerful beyond imagination. Where does that power come from? What turns stone, water, and air into a living, changing planet? First, inner heat, born in Earth's violent birth and sustained by radioactive decay, keeps the interior churning. Second, plate tectonics, great slabs of crust that drift, split, and collide, building mountains and fueling volcanoes. Third, the partnership of atmosphere and oceans moves energy around the globe, shaping climate and weather. And fourth, life itself, tiny to titanic, reshapes air and rock in feedbacks that can steady or tip the world. This journey follows those four engines, from birth to now, to watch Earth make and remake itself. From the silent vantage point of space, our world awakens. But this serene beauty belies an almost unimaginable power. Have you ever considered how a single planet can generate enough force to shift continents, raise mountains, and melt solid rock? This power flows from four interconnected sources: the planet's deep interior heat, the slow, inexorable dance of plate tectonics, the dynamic systems of our atmosphere and oceans, and in a profound feedback loop, life itself. To understand our home, we must first understand its power. Our story begins 4.6 billion years ago in a vast cold cloud of interstellar gas and dust. This solar nebula contained the raw ingredients for creation: hydrogen and helium, enriched with heavier elements like carbon and iron forged in the hearts of long-dead stars. Within this slowly rotating cloud, gravity began its patient work, pulling these scattered particles together. Over millions of years, the cloud contracted. At its center, immense pressure ignited a celestial firestorm, our sun. While over 99% of the material was consumed, a small fraction flattened into a vast, spinning protoplanetary disk of leftover gas and dust. Within this disk, a new chapter began. Microscopic dust grains stuck together, forming pebbles, then kilometer-sized planetesimals. In a chaotic cosmic derby, these bodies collided, with the largest gravitationally sweeping up more and more material. Through this accretion, our Earth was born. The energy from constant collisions melted the entire planet into a global magma ocean. This heat was supplemented by a powerful internal engine: the decay of radioactive isotopes like uranium, thorium, and potassium. This radioactive furnace continues to burn today, keeping Earth's heart fiery. But the young Earth was not alone. It shared its orbit with a Mars-sized protoplanet, Theia. Their paths crossed in the most violent event in our planet's history. Theia struck Earth at a glancing angle, blasting a colossal cloud of molten rock into orbit. Gravity pulled this ring of superheated debris together, and from the wreckage our moon was formed. This giant impact tilted Earth onto its axis, giving us seasons. In the aftermath, differentiation accelerated. In the molten Earth, the heaviest elements, iron and nickel, sank to forge the planet's metallic core. Lighter silicate minerals floated upward, eventually cooling to form the thick mantle and a fragile, primitive crust. The new moon, orbiting much closer than today, exerted a tremendous gravitational pull. It raised colossal tides in the magma ocean, and later, the first seas. This tidal flexing helped stabilize Earth's wobble, and may have helped kickstart the movement of the crustal plates that would define our planet's future. As millions of years passed, the surface cooled and a solid crust hardened. But beneath this thin shell, the internal heat engine never stopped. It creates massive, slow-moving convection currents within the mantle, a planetary-scale lava lamp operating over eons. The crust is broken into enormous tectonic plates, carried along by these mantle currents. This process, plate tectonics, is our world's master architect. Where plates pull apart, new crust is born. Where they collide, they can thrust up mountain ranges, or one can be forced beneath the other, melting back into the mantle, triggering earthquakes and volcanoes. Crucially, this restless geology makes Earth a living world. Volcanic outgassing built our early atmosphere and oceans. Tectonics recycles essential nutrients from the planet's interior. It creates dynamic environments like deep-sea hydrothermal vents, which may have been the cradle of the first organisms. Without this internal power, Earth might have become a static, barren rock. Instead, it became a vibrant, evolving home for life. On the scorching plains of the Afar Depression in East Africa, there lies a rare window into Earth's fiery heart. Here, at a volcanic shield known as Erta Ale, a lake of lava has persisted for more than a century, one of only a handful on our planet. The molten surface churns constantly, fed by a plumbing system that taps magma reservoirs miles below. Scientists who travel to its rim risk intense heat and toxic gases, yet the view rewards them with insights into the powerful convection that shapes the Earth. At night, when temperatures fall and the glow intensifies, the lake's motion becomes clear. Fresh lava wells up on one side, spreads across the surface, cools to form a dark crust, and then sinks at the opposite edge. The entire cycle is a miniature version of the currents circulating through the mantle. Such heat not only feeds volcanoes, it also releases gases that helped build our atmosphere. Without volcanic exhalations of water vapor and carbon dioxide in Earth's infancy, our planet might have remained a frozen rock. The earliest oceans condensed from steam, and over eons, volcanic gases created a greenhouse blanket sufficient to trap warmth under a faint young sun. Far across the ocean, another landscape tells a very different story of fire and water. In Mexico's Yucatan Peninsula, deep sinkholes called cenotes pockmark the limestone bedrock. At first glance, they seem like tranquil, sapphire-colored pools in the jungle, but from above they form a circle more than 180 kilometers wide, the ring of the Chicxulub crater. 66 million years ago, a 10-kilometer-wide asteroid slammed into this coast, blasting a hole 30 kilometers deep. The impact vaporized rock and sent shockwaves around the globe, triggering wildfires and a global winter. It ended the age of the dinosaurs, paving the way for mammals to rise. Today, divers explore these cenotes to map the subterranean rivers and cave systems that connect them. Some caverns contain evidence of the impact, shocked quartz and melted glass. Others preserve a record of later climate changes, with stalactites that grew during glacial periods. Though few humans have visited these drowned caves, they remind us how intimately Earth's geology and life are linked, and how cosmic events can reset the clock on evolution. In the far north, stretching across Siberia, Alaska, and Canada, a vast and frozen landscape hides a critical warning for our planet's future. This is the realm of permafrost, ground that has remained frozen for at least 2 consecutive years, and in some places for millennia. Beneath this seemingly barren soil lies a colossal reservoir of carbon. It's a subterranean vault, holding the preserved remains of plants and animals that lived and died during the last ice ages. The intense cold has acted like a planetary-scale freezer, halting the natural process of decomposition. Scientists estimate that the Arctic permafrost holds nearly 1.6 trillion metric tons of organic carbon, almost double the amount currently present in our entire atmosphere. For now, it is locked away, inert and harmless. But as the Arctic warms at a rate 2 to 3 times faster than the global average, this ancient freezer is beginning to fail. The thaw is not a gentle process. It destabilizes the ground, causing it to slump and collapse. and as the ice melts, it exposes this long-dormant organic matter to a new generation of microbes. Awakening from their own frozen slumber, these microorganisms begin to feast on the carbon-rich material. In waterlogged, oxygen-poor environments like thaw ponds, they produce methane through anaerobic decomposition. Methane is a super-potent greenhouse gas. While it has a shorter lifespan in the atmosphere than carbon dioxide, persisting for about a decade, its warming power is immense. Over a 20-year period, a single molecule of methane traps over 80 times more heat than a molecule of CO2. And now, this powerful gas has begun to bubble up from the beds of newly formed lakes that pockmark the thawing tundra, a visible sign of the deep chemistry being unlocked. To quantify this release, scientists venture out onto the frozen lakes in the depths of the Arctic winter. They clear away insulating layers of snow to reveal the transparent ice below. What they find is a stunning and unsettling record of the gas seeping from the lakebed. Bubbles of methane, frozen in their ascent, are trapped in layers like stacks of crystalline coins, each layer representing a different freezing event. By mapping these bubble clusters, they can estimate the volume of gas being released. The proof of the gas's identity is both simple and dramatic. Using an ice pick and a lighter, they can puncture a trapped bubble. The released gas ignites with a sudden whoosh and a brief, ghostly blue flame, a stark demonstration that the carbon from a long-extinct ecosystem is now re-entering the modern atmosphere as a powerful, flammable fuel. This is the mechanism of a dangerous climate tipping point. Increased warming thaws more permafrost, which releases more greenhouse gases like methane and carbon dioxide, which in turn causes even more warming. It's a self-reinforcing cycle. From space, satellites use radar and optical sensors to track the proliferation of these thaw lakes, revealing that thousands of new ones are appearing across the Arctic. This remote sensing provides a planetary-scale view of a process that could significantly accelerate global climate change, a vast carbon release that is one of the great uncertainties in our planet's future. Half a world away, another form of ice is undergoing an equally profound transformation. The Greenland ice sheet, a relic of the last ice age, is a continent-sized mass of frozen water. It's so vast that if it were to melt entirely, global sea levels would rise by more than 7 meters. And now it is melting at an accelerating rate. Each summer, the 24-hour sun creates a landscape of stunning turquoise melt ponds on the ice sheet's surface. But these beautiful features have a dark side. The dark water absorbs far more solar energy than the reflective white ice, creating localized hotspots that accelerate melting further. This water doesn't stay on the surface for long. It finds and enlarges cracks in the ice, carving deep vertical shafts called moulins. Water then plunges down these chasms, sometimes for over a kilometer, tunneling all the way to the bedrock below. This immense volume of water acts as a lubricant at the interface between the ice and the rock. It can even hydraulically lift the entire glacier by a few centimeters, dramatically reducing friction and allowing the ice to slide more easily. This process is supercharging the ice streams, fast-flowing rivers of ice embedded within the slower-moving sheet, which act as conveyor belts, transporting ice from the interior out to the ocean. The consequences are staggering. Ice that once moved at a crawl can now flow faster than we ever imagined possible. Satellite measurements tracking the movement of surface features show that some of Greenland's major outlet glaciers, like the Jakobshavn, have doubled or even quadrupled their speed in just the last few decades. As these glaciers accelerate, their terminus, or grounding line, the point where the ice lifts off the bedrock and begins to float, retreats inland. This retreat can trigger further instability, committing even more ice to be lost to the sea, directly contributing to global sea level rise. To truly understand these complex dynamics, some scientists take a more direct approach. In both Antarctica and the high Arctic, they descend into the heart of the glaciers themselves. They explore surreal, cathedral-like ice caves, carved not by geothermal heat, but by the very same surface meltwater that forms moulins. Equipped with headlamps and climbing gear, they venture into a world of sculpted blue ice to witness firsthand how these colossal structures operate from the inside out. Deep inside, near the glacier's base, the ice is no longer pure. It is a dirty, powerful tool of erosion. Here they find layers filled with rocks and debris plucked from the mountainsides. This is nature's sandpaper. Massive boulders, some as large as a house, are locked in the ice's grip, grinding and scraping the bedrock below as the glacier inexorably moves. This process of glacial abrasion, acting over thousands of years, is what carves the iconic U-shaped valleys and deep fjords that define so many of our planet's mountain landscapes. They also discover that even far from the base, the ice is not uniformly solid. They find pockets of liquid water and intricate brine channels, which act as internal weaknesses, softening the ice and allowing it to deform. These discoveries are crucial. They help explain the dual nature of a glacier. On the surface, it is a brittle solid that fractures to form deep crevasses. But under the immense pressure of its own weight, the ice deep below behaves like a viscous fluid, bending and flowing over the landscape. It is this combination of brittle fracture and ductile flow, of surface melting and basal sliding, that makes ice one of the most powerful and unpredictable forces on Earth, a force that is now responding rapidly to a warming world. Earth's story of water is one of disappearance as well as abundance. The familiar map of our world is merely a snapshot in a long and dramatic geological history, a history where entire oceans can vanish from the face of the planet. One of the most dramatic of these events began around 6 million years ago. Tectonic forces, driven by the collision of the African and Eurasian plates, pushed up the land around the Strait of Gibraltar. This uplift, combined with a global drop in sea level, eventually sealed the Mediterranean off from the Atlantic Ocean. With its only source of water gone, the relentless sun began its work. Over thousands of years, the sea vanished, leaving a desolate, hyper-arid desert crusted with salt. This new landmass, reaching 3 to 5 kilometers below the world's oceans, became a landscape of profound extremes. As the sea level dropped, rivers like the Nile became colossal waterfalls, carving immense canyons into the exposed seabed, scars still visible today in seismic data, hidden beneath the waves. The evidence for this Messinian salinity crisis is written directly into the rock. Beneath the modern Mediterranean lies a salt layer over a kilometer thick. In caverns deep beneath Sicily, miners still carve this legacy, walls of pure halite, or rock salt, remnants of that catastrophic drying. Elsewhere, giant translucent crystals of gypsum formed where the last super-concentrated brines mixed with hot groundwater. These beautiful minerals, now sealed in dark rock chambers, are the crystallized tears of a dead sea. But the story wasn't over. Around 5.3 million years ago, the dam at Gibraltar gave way. This was the Zanclean flood, a cataclysm on an unimaginable scale. A waterfall 100 times the volume of the Amazon River roared into the basin. In what may have been less than 2 years, a geological instant, the Mediterranean was refilled, and the sea we know today was reborn. The story of the Mediterranean is a powerful reminder that even vast bodies of water are not permanent. This same principle of precarious balance applies to entire planetary environments. The fates of our neighbors, Mars and Venus, serve as stark illustrations of how different the outcome can be when this balance is tipped. Mars, smaller and with weaker gravity, couldn't hold its early atmosphere. The solar wind stripped it away, plunging the planet into a deep freeze. Its thin air provides little warmth, leaving the surface at an average of 60 degrees Celsius. The channels we see are ghosts of rivers, their water now gone or locked away as ice. Venus suffered the opposite fate. Closer to the sun, its oceans boiled, filling the air with water vapor, a potent greenhouse gas. This triggered a runaway feedback loop that left a crushing toxic inferno, with an atmosphere 90 times denser than Earth's and temperatures hot enough to melt lead. Earth occupies a rare middle ground. Our atmosphere contains just enough greenhouse gas to maintain a temperate climate, a balance regulated by the planetary thermostat of the carbon cycle. But geology is only half the story. Life itself transformed our world. Early microbial life flooded the atmosphere with oxygen, creating the air we breathe and building the ozone layer, a vital shield against the sun's radiation. This protective envelope also burns up most incoming meteoroids, while our planet's magnetic field deflects the solar wind, preventing our atmosphere and oceans from being stripped away into space, the fate that befell Mars. The interplay between a planet's geology, its oceans, its atmosphere, and the life that inhabits it is an intricate and delicate dance. The stories of a dried-up sea and burnt or frozen worlds show us that habitability is not a permanent state. It's a dynamic equilibrium, where even small changes can push a world toward a hothouse or a deep freeze. For billions of years after Earth cooled, life remained simple. In shallow seas, communities of cyanobacteria built dome-like structures called stromatolites. These microbes use sunlight to split water and release oxygen, gradually enriching the atmosphere. For over 2 billion years, stromatolites dominated the fossil record. Their patient work set the stage for multicellular life by pumping oxygen into air and sea. Yet climate would throw life a challenge of unprecedented severity. Around 700 million years ago, the planet is believed to have entered a series of ice ages so extreme that glaciers reached the equator. Rocks formed in these times contain dropstones, large pebbles and boulders embedded in fine marine sediments that could only have been carried there by icebergs drifting in tropical oceans. These snowball Earth events might have come and gone, but they stressed the biosphere in ways that ultimately spurred innovation. As the glaciers retreated, nutrients poured into the oceans and oxygen levels rose. In the aftermath, life diversified dramatically during the Cambrian explosion, giving rise to animals with shells, eyes, and complex bodies. Earth has faced even darker hours. About 252 million years ago, volcanic eruptions in Siberia unleashed gases that warmed the planet and triggered the greatest mass extinction in history. Rising temperatures slowed ocean circulation, causing large parts of the deep sea to stagnate. In the absence of oxygen, bacteria that thrive in anoxic conditions multiplied, producing hydrogen sulfide, a poisonous gas that smells like rotten eggs. Evidence from ancient sediments shows that this gas seeped into the atmosphere, bleaching rocks and destroying the ozone layer. Marine life suffocated, and up to 96% of species perished. On land, forests withered under a lethal haze. Survivors were few, but from this devastated world emerged new groups of animals that would dominate later ages. Lessons from that catastrophe resonate today. Earth's oceans and atmosphere are intertwined, and tipping them out of balance can lead to rapid, irreversible change. Even now, dead zones appear in coastal waters where fertilizer runoff and warming induce anoxic conditions, a haunting reminder of ancient killers. As we consider Earth's extremes, human beings themselves illustrate the boundaries of adaptation. High in the Andes, villages perch at altitudes where the air's oxygen pressure is nearly half that at sea level. For indigenous people whose ancestors have lived there for millennia, life proceeds as normal. Their bodies have adapted with greater lung capacity and more efficient oxygen transport. But historical accounts tell of European settlers unable to carry pregnancies to term. Babies miscarried until parents sought lower elevations. Only by mingling with local populations did they acquire the genetic traits needed for high-altitude survival. Our species thrives within a narrow envelope of environmental conditions. Too little oxygen, too much heat, or too little can push us beyond our limits. Yet, through curiosity and technology, we extend our reach. We dive into cenotes, drill into glaciers, and send probes to Mars and Venus, all to understand how planets work. In this cosmic perspective, Earth is both familiar and extraordinary, a dynamic world shaped by fire, ice, air, and time. Its history is written in lava flows, salt beds, ancient reefs, and meteorite scars. By studying them, we see not only how Earth came to host life, but also how precious and fragile our planetary home truly is. Thanks for joining us on this journey through the incredible power of our Earth. If you enjoyed exploring these wonders, please leave a comment, give this story a like, and subscribe to the Physics and Cosmos Academy so you never miss our next adventure. Your support helps us continue sharing the marvels of the universe with curious minds.